Mikhail, who's going to talk about truncated wedge problems.
Yeah, thank you very much. I would like to speak about two things. First of all, I would like to explain what is the object which is called functional integral equations and how this object appears in the diffraction by some boundary which is a polygonal actually boundary. And second goal of my talk is to explain, of course, the corresponding mathematical approaches and tools that will enable us to treat these kind of equations. And probably I would like also to explain how these kind of problems may be connected with the Riemann-Hilbert problem of factorization or something like that. On the other hand, I would like to consider a relatively simple problem. This problem is nothing more but diffraction by a truncated wedge or a truncated angle, because we shall consider 2D problem. And before starting my explanation dealing with the new object that I would like to describe, I will make the following introduction and the next general remarks. First of all, it is well known that in order to obtain, for example, Wiener-Hopf equation on Riemann-Hilbert problem or their equivalents, you need some kind of transform. You transform your problem to some spectral space, and then you discuss some equation in that spectral space. And for the diffraction by a polygonal domain, sometimes you can use different kind of transforms. First of all, I should mention the methods which are based on the Fourier transform, and we could mention such researchers like Gautezan, and also the result by Lebeau and Croisil, and you can find many other people that were involved in these techniques. The second transform, which is also used, for example, for such kind of polygonal domains and diffraction in these domains, we can also mention Kontorovich-Lebedev transform. And the advantage of this transform is that you can immediately reduce your problem, boundary value problem or diffraction problem, to some integral equations or without any additional work. In this case, you can mention, for example, works of Rollins and Jones. They considered penetrable wedges or penetrable cones by means of Kontorovich-Lebedev. Also, I would like to mention our recent paper, which is devoted to double wedge or shifted wedges. For example, here we have one wave speed, and here we have another wave speed, which is separated by this ray. The third technique is, of course, very famous and widely applied Sommerfeld-Malyuzhinets technique, and the corresponding Malyuzhinets functional equations that appeared, that traditionally appear in this technique. After that, if you can't solve these equations explicitly, which means in quadratures, then you can reduce them to some integral equations. And of course, for example, some important results have been obtained by Budayev when he studied elastic wedge problem, and also some summaries or some surveys can be found in the following works also. By the way, we also should mention an important development of Sommerfeld-Malyuzhinets technique given by Bernard. And actually, my approach will have a lot of similarities with that given by Bernard, but it's not the same. And that is why for example, our approach will lead to some functional integral equations instead of simple Sommerfeld, instead of not simple but system of Malyuzhinets equations. But nevertheless, I should say, of course, we shall have some similarities with that approach given by Bernard. I also should mention the modified Wiener-Hopf technique, and due to Danieli, Lombardi, and Zich, you can find some new results dealing with applications, some new structures, some diffraction by more complicated domains. So, to my mind, it's really interesting and nice approach. It's also important to mention two other, maybe not so widely known approaches. One of them is by focus. For example, you can see some results on at least some attempts to solve the problem of diffraction in a polygonal domain. You can mention this work and also some relatively recent work by Focus and Spence. Also, as I know, there are some results by Professor Eads, has been also recently obtained by means of this focus approach. And this approach is based on Lax pairs and simultaneous spectral analysis. Also, I would like to mention some interesting results dealing with probabilistic approach by Budaev and Borgi. Now let us turn to the formulation of the problem. We have this kind of problem. We have a truncated angle, which I call truncated wedge. Also, it consists of two domains, omega 1, this is this angle, and also omega 2, this another angle. And I would like to draw here an artificial boundary, because my formulation will also include some continuity condition across this artificial boundary. We have plane wave incidence, we have polar coordinates in omega 1 and polar coordinates in omega 2. So actually we deal with the following diffraction problem. The total field in omega 1 consists of the incident plane wave, this is plane wave in polar coordinates, and some scattered wave. And in omega 2 we do not extract incident wave, but we consider V as a total field. The total field satisfies the Helmholtz equation, and for simplicity, in order to have non-trivial but as much as possible simple problem, we consider perfect wedge, which means that Dirichlet boundary conditions are valid on the semi-infinite sides, here and here, and Neumann boundary condition is valid on the finite segment of the boundary. Also, I would like, as I have said, two continuity conditions across the artificial boundary sigma 2 prime. Now we also, of course, add some Meixner-type conditions. We fix, or at least we terminate the behavior at the angular points, and some kind of radiation conditions, which here are written in an asymptotic form. We expect that at infinity we shall have the reflected wave from this side, and also some circular or cylindrical wave at infinity, which is described by this expression. And the most physically important characteristic is this diffraction coefficient. From the physical or applications point of view, you are interested basically on this, in this coefficient. This is for omega 1 domain, and this is for omega 2 domain. It can be demonstrated that this problem, if it has a classical solution in its traditional sense, then this solution is unique. So the uniqueness theorem is, of course, valid here. Now I would like to turn to my reductions. I would like to reduce, applying the Sommerfeld-Malyuzhinets technique, I would like to reduce my problem to some kind of functional, in my case it will be functional integral equations. What can be done? We are looking for the solution in the domains omega 1 and omega 2 in the form of the Sommerfeld integrals. This is quite traditional object, where gamma is the famous double loop Sommerfeld contour, which is drawn here. Gamma plus and gamma minus are two loops of the Sommerfeld contour, and we have such kind of representation for the total field in both domains, gamma omega 1 and omega 2. Also some additional conditions of regularity of the Sommerfeld transformants f and g. I call these functions in the integrand Sommerfeld transformants, and of course I should fix a class of functions in which the further solution will be found. Of course, these are some kind of traditional requirements. For example, the Sommerfeld transformant f should have a prescribed pole with a given residue in some strip, and also in this strip it should have some kind of estimate due to the Maxner condition at the edge. It should be said that we are working in the class of meromorphic functions f and g. I have no time actually to discuss the details dealing with the some specific things dealing with the derivation and with the description of the class of function, but in this case they are more or less traditional. Now I would like to write the so-called inverse transform to the Sommerfeld integral. This is results which deals with the known Malyuzhinets theorem on inversion of the Sommerfeld integral. It shows that, for example, such combinations of the Sommerfeld transformant can be expressed by means of the wave field on some line. So this is a kind of theorem. So we have plus if we deal with the total field, and we have minus if we have here total field, and we have plus if we work with normal derivative of total field. The same is valid for the second Sommerfeld transformant G, and it is remarkable that in such form we can easily apply, for example, Dirichlet boundary condition on the side sigma 1. We can only put phi equal to the value on these sides, which is phi big, and we use the Dirichlet boundary condition, and we obtain this functional equation, which is satisfied by the unknown function f. In the same manner, you obtain the functional equation due to the boundary condition on this semi-infinite part of the boundary. And a bit more work is necessary in order to obtain the boundary condition which follows from the continuity of the normal derivatives here and from Neumann condition here. This boundary condition has the following form. Because here we use one system of coordinates, of polar coordinates, here we have different system, so we have a kind of shift. This length of this segment is A, so we obtain such a specific analytic coefficient in these functional equations. And the most non-trivial equation will arise when you consider the second continuity condition. I mean the continuity of the wave fields across this sigma 2 prime. And in this case, you can use the representation of this kind. You split the integration contour into two parts, this one and this one. Then you denote the integral over the finite part of along the corresponding boundary as chi 0, and here you make some substitution and you use continuity of the wave field, and finally you arrive to this kind of formally to this kind of functional equations with some unknown chi 0. So this functional equation has such form. It looks like inhomogeneous functional equation, but chi 0 can be expressed through this function f due to some simple derivations. This derivation is nothing more, but we can substitute the Sommerfeld integral into the expression for the total field, change the orders of integration, and we, after some simple calculation, we arrive to this integral. And finally, we obtain the system of four functional, but not simply functional, but functional integral equations, because here we have an integral operator acting on f, and in the left hand side you have some difference operators which are connected with functional equations of traditional Malyuzhinets type. Of course, at this point I should also add some additional conditions, like meromorphy of the Sommerfeld transformants, also some possibility of some prescribed poles in some strip which are responsible for the incident wave, and also some behavior at infinity. At this point, I should say that if we wouldn't have this integral term, we would have traditional or classical Malyuzhinets functional equations, but the coefficients here are entire functions, not meromorphic as usually, but entire functions. This is due to the simple boundary conditions. If you have more complicated boundary conditions, for example, like impedance or Robin boundary conditions, you will have more complicated coefficients. So, to my mind, I could demonstrate the appearance of the functional integral equations in these simpler problems. Now the question is what we can do with this kind of problem. And of course we have no chance to solve these matrix functional integral equations, but I would like to reduce this system to a more simple or well-known mathematical object. Of course, this is integral equation of the second kind, and preferably with Fredholm properties. This is our next step, to reduce this system in an appropriate class of function, of course, to some integral equations of the second kind with Fredholm property. Now, first of all, I would like to simplify this system because it has variable coefficients, these entire functions present here. But nevertheless, I would like to simplify this problem. I will denote this integral term by chi 0 as was above, and I will proceed in such a manner. I will extract some explicit meromorphic functions which contain the prescribed poles responsible for incident and reflected waves, and after some simple derivations I will arrive to this kind of system. Here I consider this integral chi 0 as an homogeneity term. The idea is simple. I would like to invert, okay, in an appropriate sense, of course, invert this difference operator, matrix difference operator, or I would like to solve this equation, system of equations with respect to high zero, and on this way I expect to obtain some integral equations. What I shall do, I recall the expression for this high zero in homogeneity term in a sense. So I introduced functions u and v small. These functions are nothing more by shifted f and g. These functions, due to these two equations, become even functions, and actually we consider this kind of functional equations now in the class of even meromorphic functions with an homogeneity term. And the reason that okay, I will explain it a bit later. Now I reduce this equation to this simpler form, and I would like to resolve some auxiliary system. I suppress the inhomogeneity term. I obtain homogeneous system of equations. By the way, this system has entire coefficients, and remarkably it has very simple and almost obvious solutions. The simplicity is due to simple boundary conditions and simple, relatively simple but non-trivial problem that I consider. The solutions of, by the way, these equations are equivalent to this kind of equations. You can, who is familiar with the Malyuzhinets functional equations, can notice that instead of cotangent here, we have here some new analytic function. It could be considered as a new canonical functional equations, in a sense similar but not exactly with the Malyuzhinets functional equation. And a simple lemma says that the desired solution has such a simple and elementary form. It is verified by the direct inspection. So after substitution, this kind of substitution, instead of u in v, which are solutions of those inhomogeneous functional equations with high zero in homogeneity term, we arrive to this kind of homogeneous, non-homogeneous equations, but with constant coefficients. And by means of traditional, more or less traditional calculations, we arrive at such solution, this simple lemma. Actually, you should use a kind of Fourier transform along the imaginary axis, and after some simple work, you arrive to this kind of integral, and this is solution of homogeneous equation. It should be appropriately chosen, and after some derivations, you obtained the representation for u0 and v0, where you have in the integral the unknown high zero, which is an entire function. You remember this is our inhomogeneity term. And finally, as an important step, we have a representation for the Sommerfeld transformant. If we have Sommerfeld transformant, we can solve the problem. And now we express this Sommerfeld transformant as an integral of this unknown function high zero, which is which you can remember some integral depending on this Sommerfeld function transformant f. So this is the way to obtain the integral equation for high zero. I would like to remark that if you have high zero on the imaginary axis here, because all the other things are elementary and explicitly given, these are also inhomogeneity factors, some known things. And then you can compute this function on the complex plane as a meromorphic function. No problem then. But this representation is valid to in some strip of the complex plane. Similar expression is valid for G. And now I would like to recall you that high zero is connected with f. When you substitute instead of f in the right hand side this expression, then then you can change the orders of integration which is justified. You arrive to this kind of integral equation of the second kind, where chi 0 is expressed through xi, and you have second order integral equations with the kernel, which is given by an integral of some elementary functions. It's not very difficult to compute these things, but in my case, the integrand is elementary function because of simple boundary conditions. No, even in this case, you have no any Malyuzhinets-type functions or special function in the kernel. It can be demonstrated that this integral equation is Fredholm. Moreover, you can prove that the kernel is square integrable, which is this kernel is of Hilbert-Schmidt class, and due to the uniqueness theorem of the boundary value problem, this integral equation is not only Fredholm, but it's uniquely solvable in L2. And finally, we can show the expressions for the diffraction coefficients of these waves, which goes from the truncated wedge at infinity. At infinity, truncated wedge looks like simple wedge, and you have this kind of circular wave. Also some reflected waves, but it's not so interesting. They are simple. And the reflection and the diffraction coefficients are given by such simple formula. To conclude, I would like to say a few words about different kind of functional equations that arise in different branches of physics or diffraction theory and in mathematics. I would like to mention, for example, famous Malyuzhinets equations with cotangent. This is equations of the first order. We derived in our talk functional equations of the first order, but with different coefficients. For example, the famous functional equations, Harper equation in the quantum physics of a solid body. This is spectral parameter. This is potential is cosine. This is another parameter. Complex Maryland equation, also with nice properties. This is potential is cotangent. This is spectral parameter. For example, an Anderson effect could be observed for these equations. Also, gravity waves on fluid in its full special form, you can encounter this kind of equation. In this case, this meromorphic function is ratio of associated Legendre functions at its derivative. And by the way, in the diffraction by a circular impedance cone, you have this kind of functional equation. This equation is of the second order. So finally, I think that I could demonstrate that all these objects have really nice and important these objects are really important for diffraction theory. Okay, maybe that's all. Thank you.
Questions? Comments?
How do you prove the unique solvability of
Okay, it's better to say the following. If you have, for example, there are some, of course, delicate points, but roughly speaking, you have, if you have homogeneous equation of this kind, that the number of solutions is finite. If you take one of these solutions, by means of explicit formula, you go to your diffraction problem, and you see that the homogeneous diffraction problem has only trivial solutions, which contradicts to existence of a non-trivial solution of the Fredholm equations. This is quite traditional, I think.
Yeah.
So.
Any restrictions for the action of incident?
No, this is only for definiteness. To you can have such as oblique incidence, even you can consider very skew or very oblique along maybe one side. It's also possible.
And actually, the previous question, where you have to formulate radiation conditions with a limited absorption principle, but some restrictions.
You see, these are some delicate things. In order to apply, to prove uniqueness theorem, you should subtract all the reflected waves and some other delicate things, for example, half-shadow directions. After that, the difference of two solutions satisfy radiation condition in integral form, and then you can prove uniqueness of the initial of the boundary value problem. This kind of approach. Yeah.
Do you need tip conditions, any tip conditions to prove uniqueness?
Of course, sure. I mentioned Meixner type of condition. If you consider classical solution of the problem, you should inevitably postulate some tip condition, some radiation condition, boundary condition, and you should assume that your solution is from C2 class and also some other additional things. It's quite.
What is it like you had two Dirichlet conditions in Neumann, right?
Yeah, but it's remarkable thing. If A goes to 0, our system of functional equation degenerates to traditional Malyuzhinets equation, which can be solved explicitly. It's obvious because in this case you have only perfect wedge and nothing more. It's not surprising that this artificial system of functional equation is solved explicitly in the limiting case when A goes to 0. It can be verified.
Okay, let's thank the speaker again.
Thank you.